So welcome to the Chemistry of Air Pollution uh, lecture. We're going to look at, if you look at the issues that we face with respect to air pollution, you can look at local issues such as industrial or photochemical smog. You can look at regional issues such as acid deposition. And you can look at global issues such as climate change and stratospheric ozone depletion. Today, we're primarily going to focus on local and regional issues, although we will touch upon some of the things dealing with climate change and also stratospheric ozone depletion. So at the beginning of the year, we went through some of the basics dealing with chemistry concepts, what atoms are, what's in the nucleus, atomic number, mass number, isotopes. When we went through isotopes, we went through the different isotopes for hydrogen and looked at the idea of nuclear fusion, the ions, nomenclature for those, how you write those. We looked at radioactive isotopes, uses for those, both in things like weaponry, energy, and also medical uses. The idea of half-life. We looked at the various emissions that you can get, both alpha, beta, and gamma. Your least penetrating were alpha, and in chemistry you may have gone through I believe it was Rutherford that did the experiment that found that the nucleus was that very dense positively charged center. Alpha particles are equivalent to like a helium nuclei, beta particles are equivalent to an electron, and gamma particles are the most penetrating and the ones that are the highest energy. And again, we looked at nuclear reactions. We looked at the idea of nuclear fission, which is breaking things apart, larger things to smaller things, such as what goes on at a nuclear power plant, and also nuclear fusion, which is from smaller to larger. The sun is maybe our largest fusion plant around, and we looked at those with respect to isotopes of hydrogen, how deuterium and deuterium can be used to produce helium nuclei, or how deuterium and tritium can be used, again, to produce a different isotope of helium and neutrons. Gram per gram, nuclear fusion is about 10 times more energetic than nuclear fission. We also discussed problems with nuclear waste when we were looking at energy, differences between high-level and low-level wastes, and issues dealing with their storage. Does anybody have any questions on that? Yes?
You said nuclear fission is 10 times more powerful?
No, I said nuclear fusion gram per gram is 10 times more energetic than nuclear fission. But as we discussed, we don't have a containment vessel to put that substance in, so there's not a lot that we can do with that. Yes?
You say that the alpha beta.
So again, high-level waste and low-level waste. High-level waste you have to store for a much longer period of time, plus it's higher energy being emitted. Low-level waste is less of a problem, shorter half-lives, and those types of things. Just to go back to alpha particles, even though they're the least penetrating, remember that when you look at radon-222, it decays to polonium, I think polonium-219, and that's an alpha emitter. So even though it's emitting low level, if you will, on the scheme of things, low energy radiation, still if you're breathing it and those alpha particles are bombarding your lung tissue, you can get lung cancer. And that's why radon exposure is a reason why people get lung cancer that have not even smoked cigarettes. We also looked at, with respect to chemistry, different types of bonding, both ionic and covalent bonding, and talked about hydrogen bonding and how hydrogen bonding also gave water a lot of its very special properties. We looked at the differences between inorganic and organic compounds and did mention that just because you contain carbon does not mean that you're an organic compound, as is the case with carbon dioxide or carbon monoxide. Those compounds do not have that carbon-hydrogen bonding structure. When we talked about the biogeochemical cycles, we looked at biologically important organic compounds and the tie-in to those different components in those cycles, those macromolecules that are essential for life. We've also discussed the idea of pH, how pH equals the minus the log of your hydrogen ion concentration. The scale is 0 to 14, with 7 being neutral. So does anybody have any questions on that? So let's start to look at what's in the atmosphere. And you've had different study guides that we've worked with that break down the components of the atmosphere. Our atmosphere is dominated by, so when you look at the components of our atmosphere, also remember that when you look and we have nitrogen molecules or oxygen molecules, nitrogen and oxygen are both examples of diatomic molecules. When they exist by themselves, they exist as that molecule. It doesn't mean they exist like that in compounds, as you've seen numerous times. We have a little bit of argon left. Water vapor will vary, and carbon dioxide is a component, a dry component of our atmosphere, and the amount of carbon dioxide in the atmosphere will vary, remember, seasonally, depending on whether it's growing season or a dormant season for most vegetation. When you look at the components of the atmosphere, some people think today's atmosphere is actually our second atmosphere, but negating that, the original atmosphere on the planet, if we go back 4.6 billion years ago, was an atmosphere that was dominated by hydrogen, and it was known as a reducing atmosphere. And because of those conditions, large organic molecules were able to form. And as those large organic molecules formed, you had things like amino acids forming. So essentially you had the precursors for life and those essential compounds being formed in that primordial ooze that kind of existed at that point in time. It wasn't until somewhere around 3 billion years ago that we started to have any kind of photosynthesis occurring. And once photosynthesis occurred with cyanobacteria, algae, and your first primitive plants, you could begin having oxygen building up in the atmosphere. And probably at about 400 to 650 million years ago, we started to have oxygen at the current levels that we see today. So the atmosphere morphed from a reducing atmosphere, where you tended to build up compounds, to an oxidizing atmosphere, where you tended to break down those large molecules. Remember, in a hydrogen-dominated atmosphere, you would have things like water vapor, hydrogen sulfide, ammonia, methane, carbon dioxide. All those kinds of substances would exist in your... And any other questions? So we're going back to when the Earth first formed and looking at the original atmosphere, which may or may not actually be the first atmosphere. When you look at the atmosphere on the planet, the atmosphere is divided into layers. And essentially, we really talk about 4 layers. We look at the troposphere, the stratosphere, the mesosphere, and the thermosphere. One of the defining characteristics of the atmosphere is the fact that in the troposphere, you see temperature decline with respect to altitude, but in the stratosphere, it increases. In the mesosphere, it declines. In the thermosphere, it increases. So you have that reversal in temperature profiles that leads toward the divisions that we see in the atmosphere. When you look at the dominant gases that are in the atmosphere, obviously in the troposphere, you have nitrogen, molecular oxygen, some water vapor, carbon dioxide. And you'll note that the temperature declines with respect to altitude. That's really very critical with respect to the water cycle, because if temperature didn't decline with respect to altitude, then water vapor would never condense. Water vapor would never be able to come back as precipitation or snow or any of those types of things. If you look at the stratosphere, the dominant gas in the stratosphere is ozone. And the stratosphere is where the beneficial ozone layer is located. It forms at about a height of 50 kilometers and settles out to a height of about 23 kilometers. Remember that ozone is exceptionally beneficial in the stratosphere, as it tends to filter out because of the reaction mechanisms that produce it, UVB and UVC radiation, not UVA, but UVB and UVC. In the troposphere, ozone is a photochemical air pollutant, and so it causes many problems within the troposphere, and we will talk about that. When we talk about air pollution, we talk about the troposphere and the stratosphere. That's because as you increase your height in the atmosphere, you'll find that once you're at about 30 kilometers, about 90% of all atmospheric gases are located in that region from about 0 to 30 kilometers. That's where the gases are. That's why we can talk about air pollution in those layers. The thermosphere is an interesting layer in that you get intensive ultraviolet light in that region. The atmosphere is very, very thin. It's got an exceptionally low density, and that's able to break apart oxygen molecules or nitrogen molecules. So you get weird compounds like helium ions, nitrogen monoxide ions form in that layer of the atmosphere. And you're far enough away from the Earth. Remember, gravity does hold in our atmosphere. You're far enough away from the Earth at that point for the lightest molecules to escape. One of the reasons why we really don't have a lot of hydrogen left in our atmosphere. If you contrast that with Jupiter, I think on Jupiter's atmosphere, they still have there is still a high degree of hydrogen, and look at the gravitational difference between Jupiter and the Earth. So one of the things that you notice in the temperature profile of the troposphere is that temperature declines with respect to altitude. And as we look at things that increase the likelihood of pollution occurring in a particular layer, there are several factors that influence whether or not you're going to end up with air pollution. One of them is your topography. Are you flat? Are you in a mountain area? Are you in a valley? Is air going to be able to move through, or is air going to be trapped because you're in a valley or surrounded by mountains? And to an extent, location. Are you in a coastal area? So like in South Florida, we get a land sea breeze setup that usually circulates the air. Precipitation. In places where you have high rates of precipitation, remember that precipitation tends to take everything out of the atmosphere as that water moves through, right? Water is the universal solvent. So you see that phenomenon happening. Although just because you've taken it out of the atmosphere doesn't mean that's a good thing, because now it's in your soil or your surface water. One of the things that really lends itself to trapping pollutants and causing multiple issues with both industrial smog and also photochemical smog are thermal inversions. Remember that in a thermal inversion, instead of having your normal profile of the atmosphere, and when the atmosphere, I'm really talking about the troposphere. So remember that the normal temperature profile in the troposphere is temperature declines with respect to altitude. But when you have a thermal inversion, it starts to decline, and then you get like a warm layer, and then it declines. So you have a cool layer, and then your warm layer, and then your cool layer. So you get this area of warm air that's trapped there. And that layer of warm air basically traps your pollutants in that lower level. It precludes mixing. And because it precludes mixing, you are more susceptible to having pollution episodes. With respect to industrial smog, like we see in older kind of dank cities like London. Remember, the worst smog episode that ever happened was in 1952 in London. And we've spoken about that on multiple occasions in class. And that's where at 12 o'clock in the afternoon, it looked like it was nighttime. you couldn't see pretty much in front of your face. It was wintertime. There was a thermal inversion occurring. People were burning a lot of coal, and so sulfur dioxide, particulate matter, carbon monoxide just really hung in the air. The air was just about putrid from the sulfur oxides that were there, and posed multiple problems. Remember that in that episode in London, more than 12,000 people died. And when we look at sulfur pollutions, we will again revisit the graphic that looks at kind of the rate of death compared to what occurred in London at that time. When you look at sources for pollution, and we have multiple sources of pollution, we can look at natural sources, or we can look at anthropogenic sources, right? Human-produced sources. And when you look at some of our natural sources, certainly volcanoes come into play, both with sulfur dioxide, particulate matter, some carbon monoxide, carbon dioxide, nitrogen oxides. We talked about volcanoes kind of earlier in the year and the impact that volcanoes can sometimes have on our climate, on our global climate. And we talked about the fact that when Mount Pinatubo erupted in the early 1990s, because it was such a plume of particulate matter hitting the stratosphere, that it actually lowered global temperatures by about 1 degree C for a year. If you go downwind from active volcanoes like Kilauea in Hawaii, you actually find a desert. And you find a desert because the increase in acidity in that area from the sulfur oxides being deposited there prevent things from growing. Forest fires, naturally occurring forest fires release particulate matter, NOx, carbon dioxide, carbon monoxide. And although we don't think of plants being a natural source of pollution, remember that plants emit pollen. And what's a pollutant? Something that causes a problem, if you will, or discomfort in individuals. And pollen certainly is a natural pollutant. Think about people that have allergies to pollen. Pollen is not man-made. It's a naturally occurring substance. Likewise, terpenes, which are released from a lot of conifers, are a naturally occurring substance. And ethylene released by plants. Those are both examples of volatile organic compounds that are naturally occurring that contribute to the problem that we have with photochemical smog. When you look at anthropogenic sources, most of our anthropogenic sources come from producing energy. And most of that ties back in to burning fossil fuels and the multiple pollutants that are emitted from burning fossil fuels. Certainly deforestation is another source of anthropogenic emissions. In the United States, we have the Clean Air Act, and the Clean Air Act set the NAAQS, or the National Ambient Air Quality Standards, to set standards for what could be emitted with respect to the criteria air pollutants, of which 6 have been identified and studied. And you have those both referred to in this presentation, and you also have your criteria air pollutant handout, criteria air pollutant and hazardous air pollutant handout. When you look at the pollutants that can be emitted, there are primary pollutants and secondary pollutants. Primary pollutants are those that are directly emitted from a source. And in your notes, you have multiple examples, from sulfur dioxide to particulate matter to nitrogen monoxide. Secondary pollutants are primary pollutants that have either undergone reaction with other primary pollutants to produce something else, or they are primary pollutants that have interacted with something in the atmosphere to produce something else. When you look at photochemical smog needs sunlight, or those reactions don't take place. So tropospheric ozone, or ground level ozone, is a photochemical air pollutant. It is a secondary air pollutant. Sulfur trioxide. And you may say, well, why is sulfur trioxide a secondary air pollutant? Well, it's secondary because sulfur dioxide is emitted, it reacts with oxygen, and it produces sulfur trioxide. That's why it's secondary. Both sulfuric and nitric acids are secondary air pollutants, H2SO4 and HNO3, both examples of secondary air pollutants. When you look at nitrogen dioxide, some books classify that as a primary air pollutant because nitrogen monoxide reacts with oxygen so quickly to give you NO2, but it can also be classified as that secondary air pollutant. Remember, when fuels undergo combustion, the nitrogen oxides are not produced from nitrogen in the fuel. The nitrogen oxides are produced from the nitrogen in the atmosphere. And the high temperature combustion process allows that formation, allows you to break that triple bond in nitrogen to produce the nitrogen oxide compounds. When looking at pollutants, you can also look at the idea of a point source or a non-point source. And we know that point sources are usually more economical to deal with and a bit easier to clean up. So a point source would include something like a smokestack or a tailpipe, so you know exactly where that pollutant is coming from. Unfortunately, your fingernails do not serve as a point source. Non-point sources would include things where you don't know exactly where they're coming from. So on your criteria air pollutant sheet, you have a summary of particulate matter looking at non-fugitive and fugitive emissions. Fugitive sources of particulate matter is there's not an exact place that it comes from. Maybe it's from a dust storm. Maybe it's from a fire somewhere. Maybe it's from coal burning in another country. You don't know the exact source of that, and so those are the fugitive particulate matter. Other questions? So we have our 6 criteria pollutants, and this was as a result of the 1970 Clean Air Act. Again, those standards were set for those pollutants. They include 1-hour standards, 8-hour standards, 24-hour standards to assess what's going on in a particular area. So you have carbon monoxide, NO2, and SO2 sulfur dioxide. The standard now for particulate matter that's regulated is anything that's less than 2.5 microns. Ground level ozone and lead round out your criteria air pollutants. But remember, we also regulate, although they're not part of that criteria pollutant set, hazardous air pollutants. Things like mercury, things like lead in the atmosphere, different volatile compounds are regulated under that portion known as hazardous air pollutants. Additionally, you notice that carbon dioxide is not on the list. And it wasn't until 2007 that carbon dioxide was classified as an air pollutant, and because you couldn't regulate it before it was classified as an air pollutant. And we'll look at more at that when we examine climate change more in depth. So as we begin to look at each of these criteria pollutants, we're not only going to look at the source, but also what kind of technology exists to kind of address that. How can you mitigate effects? How can you eliminate the effects? And what is the success of some of our policies have been? Carbon monoxide, typically a component of gray air or industrial smog, and we know it's produced by the incomplete combustion of any hydrocarbon, and you have multiple examples in your PowerPoint. Our main source of carbon monoxide is the transportation sector. So how is that issue addressed? Well, actually, the original catalytic converters addressed both carbon monoxide and hydrocarbons, because hydrocarbons also contributed to issues with photochemical smog. So a catalytic converter uses an oxidizing catalyst to allow that reaction to go to more of completion, and you get carbon monoxide being converted into carbon dioxide. So on the one hand, I've gotten rid of the problem of carbon dioxide, but think about it. On the other hand, if I keep things status quo, I'm still producing carbon dioxide. I'm still putting out that greenhouse gas. And again, carbon monoxide is one of those components of gray air smog. So what's the problem with it? Well, nausea, headaches, fatigue are all symptoms, and then death, if you're exposed to enough of it, of carbon dioxide poisoning. Why is that? That's because on the sites on your hemoglobin that would typically carry oxygen, those sites are now inhabited by the carbon monoxide molecule. They have a greater affinity for your hemoglobin. So if your hemoglobin has a choice, it's picking up a molecule of CO rather than a molecule of oxygen. What are the ways to decrease the carbon monoxide that's being emitted? Well, one of those is to put catalytic converters on cars. If we increase the efficiency of our processes, especially in the energy production sector, by increasing efficiency, remember, you're using less to get out the same amount, so you're producing less of those contaminants or pollutants. You can decrease fossil fuel use, or go to more efficient burning fossil fuels, like perhaps natural gas. You can switch to alternatives. We know that cars now, we have cars that are hybrids that use both gasoline and an electric engine. If you look at a lot of the commercials on TV, they're talking about how in 2025, one of the car companies is going to have 5 or 6 hybrid or electric cars to look at. So that's a way to decrease that fossil fuel use, although it does depend on where your electricity comes from. When we talk about something being a point source or a non-point source, it's also important to think about, is this a stationary source or is this a mobile source? So when you look at a smokestack on a power plant, that's not going anywhere, right? You know exactly where that is. But if you have emissions coming out of your tailpipe, that's a mobile source of pollution. You can impact multiple areas. And you can see that we've had a good decline in the amount of carbon monoxide being emitted. The decline was about 85%. 2019 was the latest data that I could get. So any questions on that? So if we flip to nitrogen oxides, one of the main issues that we face, and although they are a contributor to acid deposition, they are the main precursor to photochemical smog. If you weren't putting nitrogen oxides into the atmosphere, you wouldn't have photochemical smog. And roughly about half is transportation and about half is from industry. Remember that when you're putting those nitrogen compounds out, those nitrogen oxides out of your tailpipe, it's not because there's nitrogen in the fuel. Again, it's because you're carrying out a high temperature combustion reaction. It allows that triple bond in that nitrogen to break and to bond with an oxygen molecule. Aside from being your main precursor to photochemical smog, it's also responsible for about 1/3 of the acid deposition that we see. And that's because the nitrogen oxides get emitted. We'll look at the reactions in a moment. And we do have some naturally occurring nitric acid in the atmosphere from the reactions of lightning in the conversions of nitrogen to nitrogen monoxide and dioxide and nitrous oxide in the atmosphere due to lightning. And again, we went through some of that with your biogeochemical cycles. As an aside, nitric acid also contributes to stratospheric ozone depletion. And that's because of competing reactions that are set up. So if you look at NOx and photochemical smog in the troposphere, ultraviolet energy is able to make it through. It rips an oxygen atom off, and that oxygen atom can react with an oxygen molecule to produce ground level ozone. And basically the ozone can react with nitrogen monoxide, generates the NO2, and that reaction can somewhat continue. The little dot next to the oxygen is an indicator that that oxygen molecule is a free radical. Remember that atoms, molecules, things like to have pairs of electrons. They don't like to have just one electron hanging out. And when that oxygen is sheared off, it has that single electron. And a free radical is a self-catalyzing agent. And that's why some of these reactions continue as they continue. Nitrogen oxides, along with hydrocarbons and ozone, can produce PAN. PAN stands for peroxyacetyl nitrate. Both ozone and PAN are both example of secondary air pollutants and of photochemical air pollutants. So what do you need for photochemical smog? You need sunlight, usually warm conditions, and you need nitrogen oxides, which are typically put out by your vehicles. You usually see photochemical smog forming in urban areas because of the number of motor vehicles in urban areas. And if you look at the sequence of events, and we'll look at the graph in a moment, nitrogen oxides are produced, NOx are produced early in the day, ozone peaks in the afternoon. VOCs you can get also from some of your different sources. When you think photochemical smog, I think the first thing that comes to mind for most people is Los Angeles. LA is in a basin, right? And that orange haze that you see is very indicative of those conditions of photochemical smog, and that's because of the nitrogen oxides in the air. NO2 is kind of a brownish, amber-colored gas that is there. One of the links that got put up for you was to look at the Science of Smog. That's on your sheet for air pollution review videos. When we're done with today's lecture, we'll let you take a look at that, and that reiterates some of what we've talked about. When you look at smog, smog is really a combination of the words smoke and fog. That doesn't really apply to photochemical smog, because photochemical smog doesn't have smoke, and usually fog is not an issue. Usually temperature inversions are a big issue. So that whole thing about smog really came out in those episodes that we saw in England and early on in the United States in the 1960s. Smog in England goes back to the 1880s when they had problems. Lousy air goes back to the 1200s, 1257. The Queen left England in the winter because the air was so disgusting, probably from all the fires and the coal burning that went on. And so you have two different graphs that look at the time dynamics for the formation of photochemical smog. And what you can see in that time dynamic is that NO very quickly with that morning traffic gets converted to NO2. And then as you move forward in the afternoon, you get the formation of ozone, or if you look at the secondary graphic, you get ozone, you get aldehydes being formed, you get PAN being formed also in that mix of oxidants that are there. And then you notice things go down at night. So you may ask yourself, well, if I have traffic at night, why am I not getting photochemical smog at night? So what's one of the big things that's missing at night that you have in the daytime? Anybody? The sun. Right, no sunlight, no photochemical smog. And those compounds are reactive, and they tend to dissipate during the evening hours. Additionally, when you look at nitrogen oxides, and just to go back to photochemical smog for a moment, and those secondary compounds that are formed, they are eye irritants, they're lung irritants, they degrade materials like rubber. Natural materials degrade. They can break down the waxy coating on leaves on plants, making the plants more susceptible to disease and also to the impacts of acid deposition. So a number of things that can happen as a result of that photochemical smog. So with respect to acid deposition, and acid deposition is really a better term than just acid rain. You can see how in the atmosphere, once the nitrogen oxides are emitted, they can be converted both to nitrous and nitric acid. Another component that can lead to that are ammonia vapors from CAFOs, from the manure that you find in CAFOs can also look to that deposition of acid rain. So what does acid rain do within the environment? And remember, sulfur oxides are more of a component, but nonetheless the results are the same. When you look at acid deposition, it can lead to essential nutrients out of the soil. It can acidify lakes. It can acidify your soil. Again, by acidifying the soil, it may kill some of the microorganisms in the soil because it may be outside of their range of tolerance. It can impact plant growth. It can weaken plants, make them more susceptible to disease because it does leach out some of those essential nutrients. Remember, we talked about when we looked at water pollution and acidified lakes, and that it can also make things like aluminum ions more soluble. That can have an impact. Those aluminum ions can, in high enough concentration, be toxic to plants. We discussed their impact on fishes. And so remember that if you have something that's acidified and you're trying to remediate, if it's a lake, you add lime to the lake, which is calcium oxide. You can add limestone, crushed limestone to the soil to help bring up the pH in the soil and remediate that increased acidity in the soil that we have. Other ways that you can reduce emissions of nitrogen oxides, if you notice, one of the first thing on our lists is always to increase the efficiency of our processes and to decrease fossil fuel consumption. Or switch to a more efficient fuel. Again, although natural gas is also a fossil fuel, is also a limited resource, as you look at a transition fuel, it certainly offers a lot of benefits with respect to being a transition fuel. And with fracking, we certainly have a lot of it. It burns at a lower temperature, so you're not producing those nitrogen oxides. You're also not producing sulfur oxides. You're not putting mercury into the environment like you would with a coal-burning power plant. So, or you can move to alternate methods. We discussed the prevalence of electric cars coming onto the market, or moving to things like wind energy or photovoltaics. If you want to increase the efficiency of your process, we talked about this earlier in the year, and it also was one of the things that you had on your air pollution study guide, and that is to use fluidized bed combustion. Fluidized bed combustion is where you're crushing the coal before you combust it, and you're mixing it at the same time with some crushed limestone. You're holding it in your furnace for a longer period of time, and because it's in that furnace for a longer period of time, you can reduce the temperature, and therefore you reduce the amount of nitrogen oxides being emitted, because you're pulverizing the coal, and the way that reaction works, you actually also have a more efficient reaction. It's also something that's used to reduce sulfur oxide emissions because of the crushed limestone in there, which kind of acts like very similar to the way that a scrubber would react. Starting in the 90s, cars had three-way catalytic converters. And the original catalytic converters just addressed carbon monoxide and hydrocarbons, and it converted those to carbon dioxide and water. So essentially they got rid of one problem, but are still contributing to a second because you're burning fossil fuels. When we started to look at decreasing acid deposition and trying to work a little bit more on photochemical smog, nitrogen oxides were a bit harder to address. You need a catalyst that's going to oxidize, be an oxidizing catalyst to get that first set of reactions to go. You need a catalyst that's going to be a reducing catalyst to take the nitrogen dioxide to nitrogen and oxygen. So it is a separate catalyst. Remember, catalysts are expensive, things like platinum, those types of substances. So the three-way catalytic converters came into play and addressed the carbon monoxide, the hydrocarbons, and also the NOx being emitted. When you look at power plants, in industry, the way that nitrogen oxides are being addressed there is by a device called a selective catalytic reduction unit, SCR, which stands for it stands for selective catalytic reduction. And it involves injecting ammonia in the reaction, but the net result is instead of putting NOx out of your stacks, you're putting out nitrogen, molecular nitrogen, and molecular oxygen. We know that the cap and trade policy has been applied to sulfur oxide emissions. They've talked about applying it to nitrogen oxide emissions, but it hasn't really been put into play at the moment. And you can see that nitrogen oxide emissions have come down. Most of those in the last 25 years, because originally they went up just a little bit. So if we look at sulfur dioxide, our major source of sulfur dioxide in our atmosphere is coal-burning power plants. Remember that coal-burning power plants are also responsible for 25% of the atmospheric deposition of mercury. Sulfur dioxide by itself is an air pollutant. It is a respiratory irritant. It is an eye irritant. A few years back, they estimated that an extra 50,000 people a year died from exposure to sulfur oxide emissions. So it can be anything that's really hard on your respiratory system, puts a strain on your heart, typically as well. So it's our main precursor to acid deposition. I think the most acidic rainfall that we saw early on in I think it was in the 60s, was 1.9 in Wheeling, West Virginia. And we've seen acid fogs as low as 2.3, 2.4. Remember, lemon juice is around 2, if you want to get an idea of the acidity, right? Normal rainfall has a pH of 5.6. You're looking at something that's, if you even went just to 2.6, you'd be looking at something 1,000 times more acidic than normal rainfall. You can get acid snow. When that snow melts, you can acidify surface waters in lakes, which can have a detrimental effect both on the fish and the vegetation in there. We not only get it from coal burning plants, but we also get it from smelting operations, which are also a source of lead in our environment. When we talked about the sulfur cycle early in the year, we did mention the smog event in London in 1952. It was a 4-day event, and close to 12,000 people died. Cardiac arrest, respiratory failure, and you can see the correlation between the high levels of sulfur dioxide and the high number of deaths. Remember, that event only lasted 4 days. And during the daytime, you literally couldn't see your hand in front of your face. It looked like nighttime at noon on the streets of London. And we saw some clips of that early on when we looked at and saw Endangered Planet. And you notice that even after those levels dropped, deaths continued because of the exposure of the individuals to those multiple pollutants that were there. So how do we reduce our SOx? So far we've talked about NOx, and now we're going to talk about SOx. Well, wet scrubbers. And we've talked about how wet scrubbers work before, using limestone in the water mist, and you're producing calcium sulfate, which drops out, and you put carbon dioxide out of your smokestack. They've talked a little bit about magnesium scrubbers, but it's not really been a go. We talked about fluidized bed combustion a few minutes ago, and that's also a way to reduce those sulfur oxide emissions. Perhaps our most effective policy came out of the 1990 Clean Air Act amendments, and that's when the cap and trade policy was implemented. In the cap and trade policy, the most polluting power plants were identified. A lot of those were in the Ohio River Valley. And the idea is that cap is a maximum amount of sulfur oxides that can come out of that area. Remember, acid deposition is a regional problem. Just because I'm producing those sulfur oxides here doesn't mean that that's where my acid deposition is taking place, because that plume of smoke moves both with the water cycle and also with air currents moving. Most of the dead lakes in Scandinavia are caused by coal burning in Western Europe. The dead lakes in Canada and in the Adirondacks are caused by coal burning in the United States in those areas. Most of our acid deposition occurs east of the Mississippi River. That's your concentration of industry in those areas. So that idea of pollution credits and cap and trade actually worked really well. Remember that if, and every year the limit becomes more restrictive so that you just can't be producing more and more and more. And the idea also behind that was if you retrofitted your facility, you had to bring it up to current standards for air pollution, and that was shot by the Trump administration. I believe it's been re-implemented. Maybe it was Bush. It might have been Bush that did that, but that was gone for a while, and now it's come back. So the idea is, say that Andrew has a really efficient power plant, and he doesn't really need all the sulfur oxide credits based on what he has, or he retrofitted and now he's more efficient. He doesn't need those credits. And say Cameron's plant is really old and is just spewing chunks out into the air. Well, Cameron can buy his credits, which allow her to not get fined, but keep that same amount of sulfur oxide coming out in the area. So it balances things out. When it was first proposed, environmentalists said, this is never going to work. Who's going to regulate it? The industry said, this is never going to work. It's going to be so expensive, we're all going to go bankrupt. And as it turned out, they both were wrong, and it's worked rather beautifully. And you can see that there's been a substantial decline in sulfur dioxide emissions. So aside from cap and trade, how can we really do this? Well, we can decrease fossil fuel consumption. We can move away from coal. Again, if you use natural gas as an interim fuel before moving to alternatives like wind and photovoltaics, you will dramatically cut your sulfur oxide emissions because natural gas doesn't have those sulfur compounds in it. You can use, again, scrubbers. You can increase the efficiency through things like fluidized bed combustion and other things that increase the efficiency of your mechanization. You can clean coal before you burn it, but that is not a very cost-effective way to go about that. It's a kind of an ineffective way to go about that. And again, things like wet scrubbers are used specifically to reduce those sulfur oxides. And acid deposition continues to be a problem for that. If we go to particulate matter next, one of the most effective ways to control emissions of particulate matter is through a device called an electrostatic precipitator. And like its name suggests, it passes particles basically through a negatively charged plate, and then it goes through collector plates that are positively charged. Those particles are attracted to it. When the field is turned off, they drop out, they can be collected, and your plume of smoke leaving your facility is devoid of those particles. There have been two classifications for particulate matter. One is PM10, which is 10 microns or less, but they found that standard was being met, a lot of it by burning open fires. And so they really looked at particulate matter 2.5 microns or less. And you can see that there have been declines. Even though a lot of those filters are exceptionally effective at taking out those 2.5 and 2 micron particulate matters, they're not so effective as taking out aerosols. And aerosols are classified as anything that's less than 1 micron in diameter. Most of those are not caught by filters, and most of those are what would do the most damage. Remember, a gas can move through your lungs fairly efficiently, but if you get particulates in your lung, those tend to stick in the lung tissue, and they can also act as a surface for other things to stick in your lungs. I'm going to look at some of the issues with those, but when you look at your particles that are maybe between 2.5 and 10 microns, so you're looking at things like ash, like dust, pollen, soot. They can cause you to cough, and you have in your nose is kind of your first line of defense, right, to trap those particles. Have you ever been out someplace where there's a lot of dust in the air and you go home and you blow your nose and you look like you're blowing out dirt, right? Your nose is, and the cilia in there, really your first line of defense. But those particles can cause lung irritation, coughing. Particulate matter can coat the leaves on plants and cut down on your photosynthetic effort. But when you look at the smallest particles, things less than 2.5, and those aerosols, those are things that can really stay in your lungs. Those are the things that cause more severe problems. And anytime you have decreased lung function, you decrease your ability to carry oxygen, you're putting more pressure on your cardiac system as well. So decreased lung function, chronic bronchitis, irregular heartbeats, heart attacks that don't kill you, and potentially premature death are all things that can occur from exposure to particulate matter. Any questions on that? Anybody out there? Yes. When you look at a lot of those things that come out of spray bottles, it's really, really tiny particles that are there. So less than 1 micron is a particle. When you spray out Lysol, that's part of your aerosols. Well, a lot of people are allergic to compounds like that, to those chemical compounds like Febreze. It just depends whether they're mostly composed of volatiles or whether it actually is those aerosols that are being distributed. So if you look at our friend ozone, remember that stratospheric ozone is good, tropospheric ozone, ground level ozone is bad. It is a secondary air pollutant, and it is a very, very strong oxidizing agent. One of the components of photochemical smog that we look at that is a substantial problem. There's a mistake on the slide. It's a lung irritant, it's an eye irritant, it breaks down materials. One of the places that ozone gets generated, not as your photochemical air pollutant, but when you look at copy machines that run, or a lot of office machinery that runs, the electrical sparks that run some of those do spur on the reactions that produce ozone. Sometimes that's why you get those smells in those areas. And you can sometimes smell ozone after lightning. It's kind of an interesting smell. But ozone is perfectly clear. Just because you have blue skies doesn't mean that you don't have a problem. It's one of those pollutants that, yes, it's declined, but not to the extent of the others. Ground level ozone declined, and your slide has a mistake. It should actually be a 35% decline from 1980 to 2019. And actually, the most notable declines came after 2002, when you really saw more vehicles have the three-way catalytic converters in there. And again, think about how topography plays a role in some of these. California is concerned. California, again, is like the poster child for what we see. And we can talk about, when you look at the National Ambient Air Quality Standards, there are hour standards, there are 8-hour standards, there are 24-hour standards. And again, during those pollution alerts, people are told not to go outside. Don't go play tennis. Don't jog. If you have little kids, don't let them out. If you have respiratory problems, it's an ozone alert day. Don't go outside. And they're seeing that ozone levels are slightly going up in the basin, and they're not exactly seen why. And if you look in 2017, they had 145 days where they exceeded their ozone standards, where people had a problem. Even in South Florida, we have problems where you're told not to go outside on occasion. A lot of it is tied in both to particulates and to photochemical smog. When you look at the air quality in an area, you can look at something called the AQI, which is an air quality index. And it takes into account particulate levels, nitrogen oxides, ground level ozone, and sulfur dioxides, and gives you a rating for that. So you can go to an air quality index for Dade County and pull up what the air quality index is in different areas. You can put in your city and find out what the air quality index is for a given city on a given day. And there's good air, there's moderate air, there's bad air, and you really shouldn't go outside air, sort of. So there is that kind of ranking for what goes on with respect to air and air quality. To round out our criteria air pollutants, we have lead. The main source of lead used to be transportation and fuel, but the main source of lead today is really metal processing. So smelting operations, where you're cooking your metal to get out your desired result. Some lead is also emitted from coal-burning power plants. Fuel used to contain lead, and it was in lead because it allowed certain things in your engine, I guess, to work better, so your engine didn't knock and your engine didn't ping. But when they put catalytic converters into cars starting in the 1980s, they had to have fuel that did not have lead. If you remember from biology, heavy metals can poison a catalyst. They can stop your enzymes from working, and enzymes are really just biological catalysts. So lead was phased out from fuel because of the fact that it poisoned the catalyst in the catalytic converter. It would make that device useless. And as you can see from your outline, it was totally banned in 1996 from fuel. I believe aviation fuel can still have some lead content in it. Lead paint was banned in 1978. However, if you look at where you find lead paint is when you look at older neighborhoods, and a lot of times when you look at areas where you have socioeconomic depression or poor neighborhoods where there's peeling paint inside houses. It's just that paint's been painted over and painted over and painted over, and that lead paint may still be there. A lot of the pigments were lead pigments. That peeling paint can be eaten by children. Pieces can break off and be really tiny, get into your soil. You can breathe them in. And remember that lead is a neurotoxin. It impacts a child's ability to learn. It can cause birth defects. Lead is a very soft, pliable metal. So go back to the Roman Empire. The aqueducts were all lead pipes. Their silverware was made of lead compounds. Their wine goblets were made of lead compounds, right? We talk about some of the people going mad. Well, think about that. They were exposed to lead. They drank a lot of probably interesting wine that was probably very acidic, leaching the lead out of those cups and putting it right into their bodies. A lot of times now when you go by a house that's an old house, people will ask to have a lead inspection to make sure there's no lead in the lead paint, because that would have to be remediated, and you'd need a professional come in. It's not something you could do yourself to remediate that lead. They used to use lead to connect different metal pipes in plumbing systems or solder, and that was banned in 1986. And I think it's been less than 10 years where lead solder was also banned on printed circuit boards. Lead is one of those areas where there has been a substantial decline in our atmospheric amount of lead. It's declined in the United States by close to 99%. So successful on that front. A group of compounds which are not part of your criteria pollutants but still do cause issues are your hydrocarbons and your volatile organics. And as we said earlier today, Those compounds can be naturally occurring, like terpenes that you get from plants, particularly conifers, ethylene that is sometimes released from plants as they undergo ripening, industrial solvents, benzenes, a lot of those types of solvents in transportation. We still see it coming from there, and they are a component of photochemical smog. Hydrocarbons in vehicles are taken care of by catalytic converters, where those hydrocarbons are converted into carbon dioxide and water vapor. And additionally, mercury is classified as a hazardous air pollutant. And there's a list of a couple of hundred compounds that make that list of hazardous air pollutants. They're not part of your criteria air pollutants, but they are a category of pollutants that looks at being regulated. Mercury is a neurotoxin, and one of the main sources for the atmospheric deposition of mercury are coal-burning power plants. Any questions so far? Yes. So we looked at the fact that both sulfur oxides and nitrogen oxides can contribute to acid rain or acid deposition. And again, that is a regional problem. You know, one of the first fixes that they had for smokestack emissions in neighborhoods was they just built taller smokestacks. Because if I build a taller smokestack, it becomes somebody else's problem and not my problem. And which way did the smokestacks blow? The wind blew them toward the poorer areas of town typically. We know that acid rain is anything less than 5.6, and certainly NOx from transportation and SOx from coal and diesel combustion do form those nitric and sulfuric acid respectively. They can leach out soil nutrients. They can make aluminum ions reach toxic levels in the soil. Other metals can also do that. We know it makes acids make heavy metals more soluble. So again, it can cause significant problems. When you look at, aside from acidification of your soils and your water and leaching of soil nutrients, remember that it can also do damage to structures. So any structure that's a marble structure, which is the metamorphic form of limestone, is going to be susceptible to acid deposition. The Taj Mahal, some of the damage there was caused by acid deposition. When you look at, and I think your book has pictures of different statues, acid deposition has caused the corrosion of those. Damages to crops, and we've talked about that before. You know, in places where you have limestone as your bedrock, you're not as likely to have your lakes or surface waters go acidic as readily, right? Because limestone acts as a buffering capacity. But in places like in the Adirondacks in New York and Scandinavia, where there's a granite base to the lake, or in what you see, those are highly susceptible to becoming acidified and dead. You know, once you start getting below 5.5, you start losing aquatic organisms. You get below 4.5, 4 to 4.5, nothing's left, and you probably have a dead lake. The other impact is on soils. You might have some potentially invasive species that's an acid-loving plant, and now that can take over and outcompete native plants that are there. And we know that to remediate, you can use lime or limestone to remediate in the soil and also to remediate in the water. And the strategies that we talked about to reduce sulfur oxide and nitrogen oxide emissions are also applicable to reducing that acid deposition. We talked about with water how you can get acid shock in a lake. How if there's a big snow melt, the snow is acidic, you can get that rapid influx into that lake and surface water and pose substantial problems. So that's our regional problem, and we've been outside now, and outside we have problems with industrial smog and photochemical smog in regional areas, in local areas, acid deposition as a regional issue. When we look at global issues involve climate change and also involve stratospheric ozone depletion. And part of that is because of how air circulates on the planet. We know from prior discussions that our major greenhouse gases are carbon dioxide and water vapor. And we don't really have water vapor a lot in the mix, right? Because water vapor only stays in the atmosphere about 9 or 10 days before it turns over, so it doesn't pose that same potential threat. Methane is a powerful greenhouse gas, 20 to 25 times more effective than CO2. Nitrous oxide, I think, is about 200 times. Remember that when you look at those greenhouse gases, we talked about the idea of global warming potential. And that's what's the warming potential compared to a molecule of carbon dioxide. Much like how the periodic table is set up based on the masses of carbon, we look at this based on the global warming potential of carbon dioxide. Freons, CFCs, those things that we phased out in the Montreal Protocol that are such ozone depleting compounds, are also a really potent greenhouse gas. They're about 10,000 times that of a molecule of carbon dioxide. And part of it is because they're so stable, they can stay in the atmosphere for 50, 60, 70 years. Why they're a substantial problem. And they're totally anthropogenic. There are no natural sources of those. Another gas, which is a greenhouse gas, is sulfur hexafluoride. And sulfur hexafluoride is used gas. It's used as an insulating agent in the electrical industry and electrical power industry. It's got a global warming potential over 100 years of 22,000 times that of a molecule of CO2. And so they are looking at substitutes for that and to move away from that. And again, with climate change, we are going to look at this specifically in more depth. We'll look at that on Thursday. So your other kind of global outside issue is stratospheric ozone depletion. And in your notes, you have the reactions for both the formation and an example of depletion by using one particular CFC or Freon, which I think was Freon 12. So when you look at those reactions, and part of the reason why I give you all the reactions is not only because I really like chemistry, but because you need to know these for the AP exam. That's why they're here. So up in the stratosphere, ultraviolet light comes through, splits a molecule of oxygen into those oxygen-free radicals. An oxygen-free radical can react with ozone. M is a third body. It just represents kind of an inner thing that's there that can be knocked around in there. It's not part of your reaction. UV light, particularly UVB or UVC, is used to help spur that reaction on, and you produce ozone, and you can see that infrared energy is kicked out. If you noted in the stratosphere, when you got to the top of the stratosphere, temperature increased with respect to altitude. It's suspected that this reaction mechanism may be one of the reasons why temperature does increase there with respect to altitude. So when you have CFCs or chlorofluorocarbons that eventually make it up to the stratosphere, and you know CFCs, freons were introduced as a refrigerant or a coolant in the 1940s. So why didn't we notice a problem until the 1970s or the 1980s? And that's because they're so stable, it took a long time for them to get up into the stratosphere. That's why we didn't notice a problem. So in the stratosphere, a chlorine free radical can get ripped off that molecule. That free radical can react with ozone to produce oxygen and chlorine monoxide. Again, you can regenerate that free radical. So one CFC molecule, one of those chlorine atoms, can destroy upwards of 100,000 ozone molecules. In earlier discussions, we talked about the fact that the thinning over Antarctica, which is our coldest place, is more pronounced in the springtime. So why is that? Well, a couple of reasons. Remember that even though the Earth is not a perfectly round object, right? It's a sphere. So if you look at the polar regions, the height of the troposphere is slightly lower in the polar regions than it is over the equator. And because of that, in those polar regions, you do get some water vapor. that you normally wouldn't get in other areas. And because you get water vapor, you can have ice crystals forming, part of the polar vortex kind of that moves through some of those areas. But you can get ice crystals forming. When those ice crystals form, they can bind up some of those chlorine atoms. And then when the springtime comes, they melt, and you get a preponderance of those chlorine atoms, which is why you would get your major thinning when those chemical species are in play. We originally saw, actually when they first saw the thinning over Antarctica, they thought it was an anomaly, but it turned out that it was real. So if you look at where population is distributed, do you have more population in the northern hemisphere or the southern hemisphere? Anybody? In the northern hemisphere. So one of the big concerns is when they started to also see that thinning in the Arctic. But the thinning in the Antarctic is what spurred on the Montreal Protocol to ban out CFCs and to find replacements. And again, we're going to look at this in a little more detail, but essentially those replacements are where you replace some of the chlorine atoms with hydrogen so the compound is less stable in the troposphere and doesn't do that same damage when it makes it up to the stratosphere. Why do we care about stratospheric ozone depletion? Well, for about every 1% decline in stratospheric ozone, there's a 3 to 5% increase in rates of skin cancer. Both and melanoma is part of that mix. It causes an increase in cataracts. That's why you see why most sunglasses and glasses will say they block out UVB and UVC. It causes a decline in your immune system. It impacts rates of photosynthesis. There's been a 10% decline in the phytoplankton population in Antarctica. And part of the reason for that is because of the decrease of stratospheric ozone. And if you take out those phytoplankton, what are the zooplankton or krill going to eat? What are your baleen whales and squid going to start eating? So it can have a ripple effect throughout your food chain and food web. Freons, CFCs, chlorofluorocarbons, same thing, one of your ozone depleting compounds. Halons, which were a compound found in fire extinguishers, which contained the bromine, were brominated compounds, and those bromines do the same thing as the chlorines when they get up into the stratosphere. One of the agricultural pesticides is methyl bromide. And methyl bromide was supposed to be phased out, but I believe the United States got an extension on that. And also nitrous oxide. So nitrous oxide, something that we can't set limits on, is both a greenhouse gas and an ozone depleting compound. And there's really no way to necessarily set a limit on that. So any questions on that? So we've talked about things that occur outside. Let's talk about indoor air pollution. Because the truth is, you're more likely to get sick or die from exposure to indoor air pollutants than you are from outdoor air pollutants. And that's because you spend the majority of your time inside. You people are house rats. So what in your house, and you have some diagrams in your textbook that look at those indoor contaminants, but you can have both natural kind of contamination in your house, as well as have anthropogenic or man-made sources of what's in a house. So one of the things that you can see occur in a house is mold. And I'm not talking about mold on bread. I'm talking about mold that typically forms because of excess moisture, or you have a leak and you've had moisture in your wallboard or something like that, and you get mold growing. One of the big issues in houses is black mold, because black mold can be toxic. Mold can be a lung irritant. It can be an eye irritant. How do you get rid of mold? Well, if it's a leak, you get rid of the source of your leak. Other ways to clean it up, potentially you might be using something like bleach on the mold to kill the molds, or a moldicide. That could be a word. Yes?
Would the indoor air pollutants be more like concentrated?
No, not necessarily. I mean, it depends where they are. But you have a greater exposure time. So whereas outside you might be exposed to something for 10 minutes, inside you might be exposed to something for 3 hours. and you have different things inside than you would outside, and part of that is concentration. If there's radium decay and you're getting radon outside, the radon dissipates into the air. But if it's in your house, it stays there, and you're more likely to come in contact with it. You get radon from uranium decay, uranium isotopes decay in the rock beneath your house, coming up through the soil. It can come up through cracks and crevices in the base of your house. Up north, they have basements. Down here, we don't really have basements because you'd have like an underground swimming pool. They have basements, and a lot of times those basements are unfinished, so it's just a dirt floor. And so radon 222 can come up. Remember, one of the issues with radon, even though it has a short half-life, it does degrade into polonium isotopes, and those polonium isotopes are solid. So you have those particles, those alpha emitters, sitting in your lung, and that's why radon exposure is a major cause of lung cancer, especially in people that are, you can see it in people that don't smoke. And more of a problem in some places than others. Some places have you check the soil for radon concentrations before selling a house or building a house. Dust is another kind of natural lung irritant, and maybe an eye irritant depending. And I guess the way you get rid of dust is, I guess you have to clean your house. Get a HEPA filter. When we look at anthropogenic sources or humans, actually another way to get rid of radon aside from sealing things is just to ventilate your structure. Let the fresh air in, and that will get rid of the radon gas. You see a lot of anthropogenic sources in the house, especially VOCs, from furniture, from carpeting, sometimes from cleaning solvents. There are some companies that when people get new furniture will come in and actually kind of heat the house up to drive off the VOCs so that you're not exposed to it. When I moved, solvents that people use, cleaning projects, people that spray tons of insecticides in their house. Those are all full of fairly nasty compounds. Cleaning products have different solvents in them depending on what you're using. And then you can also have issues with cooking. Carbon monoxide or from an improper functioning gas stove, or carbon monoxide from a faulty heater. That's why there's carbon monoxide detectors in houses, because carbon monoxide is an odorless, colorless gas. Every year, it seems during the wintertime when it's really cold, they find people dead in the house because their heaters weren't working properly, their gas heaters, and carbon monoxide was being formed. Particulate matter from cooking, and that's much more of a property or an issue in developing nations than it is in developed countries. But when wood or dung is being burned, it puts lots of particulate matter in the air, can also put carbon monoxide. Another anthropogenic or kind of human source of a problem indoors is asbestos. And asbestos was used as pipe insulation. It was used to make ceiling tiles to help them be flame retardant. Floor tiles had a percent of asbestos. And as asbestos ages, it becomes friable, which means small pieces of it can start to break off. And that's when you can breathe them in. And asbestos is associated with lung cancer. How do you remediate if you have asbestos? It's not like mold where you can go spray bleach. You really have to get someone that's a certified or a qualified individual to come in and remove the asbestos and to remediate for that, so that compound is, or that substance is properly taken out. Cigarette smoke is a source of both carbon monoxide and cadmium for indoor air pollutants. So you have a multitude of any questions on any of that?